Okay, so all right. So before we continue, so I hope everyone has chance to watch the previous lecture. And do you have any questions for the previous lecture, or the question about the practice assignment? So before we start. Okay, great. All right, let's get started. Okay, so last time we talked about how we can test the major genetic effects, right? We use the F2 population as an example. And okay, then we can use this linear model to describe the relationship between the phenotypic value and the two possible genetic effects, so the additive and the dominance. And actually, we translate this genetic problem into a statistical problem. So we use this linear model to help us to test these two major effects, right? And okay. And for each genetic effects, for example, the additive one or dominant one, we can form this F test and we can use this F statistic to help us to test whether this genetic effects, B1 means the additive effects A, right? And B2 is the dominance, which is D. We want to test if this two is significantly different from 0. So if it is significant, or any of these genetic effects is not equal to 0, which means this locus should be associated with the phenotype of interest. So this is the underlying theorem for testing the genetic effects, major effects. Okay, so we talk about different ways to set up this linear model, right? So by using the linear combination, so we can easily change the scale of the data and to facilitate our calculation. So for example, this is the traditional way we do this. We just use so I hope you still remember, we use Z to represent and the genotype that is associated, the random variable that is associated with additive effects. So for the first genotype A1, we use 1, positive 1. Heterozygous, we use 0. And for the other homozygous, the third one, we use -1. But when we use W random variable to represent the design matrix for the dominance effect, we use 0, 1, and 0. Okay, so this is the basic setting here, and we can also use different design matrix. For example, if we use this, we define like the Z variable equals to a positive square root of 2 for the first genotype, and so on. Then we can make this calculation very nice mathematically. So for example, if we define the Z and W in this way, so we can see the expectation of these two random variables is still equal to 0. However, the variance of these two are both equal to 1, and the covariance is still 0. So this is very mathematically attractive. even we change the scale of two random variables, this will not change the association between this locus and the trace, right? So we do not change any thing in the hypothesis testing. So, but by using different scales, we can significantly improve the efficiency or beauty of our coding and the computation. Okay. And this is another way. So we can even use the dummy variable to help us to do the testing, to set up the linear combination model in a different way. So this is called the dummy variable. And as you can see, eventually you got the same test results. Okay. And these two slides just show you how we can relate the results from different, using different scales of the random variables to each other. So even we use different scales for Z variable and the W variable or dummy variable, eventually we got the same test results. Okay, let's continue here. So, so last time we very briefly talked about the two types of the errors that we can commit in a hypothesis testing. So the first one is the type 1 error. Type 1 error means, I hope you still remember. So we, when we do a hypothesis testing, so the test statistic can actually following two possible distribution, right? So this one is called the H naught, means the non-distribution, and this distribution is the alternative hypothesis, which is the alternative distribution. I hope you still remember the example I showed you a long time ago. So we can treat these two as two different addresses, right? So you want to choose one from these two addresses to and go to the party. So which one should I choose? So, but we do not have time to try both on. So we just try this one. So we want to test our data if our data fit this non-model or not. All right. If the p-value is large, okay, then that means like the data fit the non-model very well. We're gonna accept the non-hypothesis without considering the alternative hypothesis. Otherwise, if the p-value is very small, when we fit our data to the non-model, or in another way, so our data doesn't fit the non-model, non-dress at all. So we're going to reject the non-hypothesis and just take the alternative hypothesis. So this is the hypothesis testing. And all right, then for any test, hypothesis testing, so we have two situations, right? Either the non-hypothesis is true, so the alternative is not true, or this is the first situation. The second situation is, all right, in the other way, right? So the non-hypothesis doesn't make sense, it doesn't fit your data. So we're gonna assume the alternative one is correct. So two situations. So these two situations actually can define these two types of errors. So type 1 error actually means if there's not an association between this locus and the traits, which means this situation, right? So if there's no association between this locus and the traits, non-hypothesis is true. But you claim there's association, so that is a mistake, right? So given the non-hypothesis is true, but you reject it, you reject the non-hypothesis, this is an error. So we call this type of error as a type 1 error. So this is aligning with this situation. Is that clear? Okay. All right, the type 2 error is describing a situation another way. So suppose your alternative hypothesis is true. So this is aligning with this case, right? If the alternative hypothesis is true, which means if there is a genetic association between this locus and the trace, however, you fail to detect. You fail to detect this association, and you accept the null hypothesis. This is another type of error. All right, I hope it is clear. So this table actually shows the relationship between these two types of errors here. So given the null hypothesis, so this table shows like, oops. So suppose this y-axis represented a true situation, and this is your test results, the x-axis in this table. All right. So given the null hypothesis is true, just this part. All right. You could either accept the null hypothesis, which is correct. So that's the probability associated with the correct decision, or given the null hypothesis is true, but you rejected the null hypothesis. So this is an error. So in this case, this alpha equals to type 1 error. So this is something that we usually see, right? Type 1 error. The alpha type 1 error. So in a usual situation, we set alpha equals to 0.05. So that's the tolerance rate. That's the maximum like type 1 error we can tolerate. All right. So that's the type 1 error. All right. Now, if the alternative hypothesis is true, I hope everyone is very clear here. So if I say the alternative hypothesis is true, which means in our business, which means there is a association between this locus, test locus, and the trace, right? So given there's an association, so we should be able to detect this association. So that's the correct decision. And the probability for us to correctly detect this association is called the power. So this part is the power. However, if the association exists, but we failed to detect this association, that's an error, right? That's the type 2 error. And this beta plus this omega, which is power, these two things should add up to 1, right? And this phi and the alpha should add up to 1 too. Does that make sense? Yeah. Okay. Any questions here? Okay. And all right, so I hope like I use this table to explain clearly the relationship between alpha, beta, and the power. Because in your future study, when you write your own paper, or if you read the articles like other people's paper, you always see this type 1 error, type 2 error, and sometimes power, right? So hopefully everyone can understand the relationship between these terms. And so once we knew the type 2 error that is associated with any statistical test, we can easily calculate the power for this test. So this is important because in the future, when you try to design your own study, you need to know the power of your study, right? So you want to know what is the probability for you to use this sample size or to use this design to detect any differentially expressed genes between the control and treatment. So this is how we calculate the power. So we use 1 minus the type 2 error. So we're gonna talk about this in details because this is an important topic for us. and this week, I'm gonna provide some like practice assignment to help you calculate a power or required sample size if you want to achieve some if you want to achieve some power, what required sample size you need to do that. So this is the topic we're going to focus on today. All right. So as I mentioned, so this is example, just a very easy, simple example. So here we, for example, so we want to test if a specific drug is effective in decreasing the blood sugar. So for example, so to test this, we got some number of the patient, and for each patient we're going to measure the pre and the post treatment, right? The blood sugar level, and so we're gonna see, like, because this is a special design, so we're gonna treat this as a paired t-test. So for each patient we're gonna look at the difference between the post and the pre treatment. And so the last column actually represents the difference, right? The difference between the post and the pre for each patient. And so if the null hypothesis is true, so what is the null hypothesis here? Can anyone tell me? So the null hypothesis is always like the no difference, no significant, or nothing, right? There's nothing changed. So in this case, if there's nothing changed, if the drug is not effective, so we're supposed not to be able to see any difference between the pre and the post, right? So if that is the case, the null hypothesis, this column should be roughly around 0. Do you agree? So this is the null hypothesis. However, if the alternative hypothesis means like, if we want to test if the distribution of this column is around 0, but the data tells us like this is not true, and this number is significant. The mean average of this column is significantly greater than less than 0. Let's say greater than 0. So actually this is pre minus post. All right. So if the average of this column is significantly greater than 0, which means there is a effect, right? There is a drug effect shown in this experiment. In this experiment. All right. So this is basically the thing we want to test. All right. And okay, so now we're gonna test if this data comes from this distribution, the blue distribution, which is the non-distribution. Can you see this? This distribution actually is surrounding the 0, right? So, all right. Or if this data, we want to test if this data actually coming from this distribution. So that's the alternative distribution. So I try to link this to our example. So here we're talking about 2 dresses, right? 2 dresses. We want to test the non-dresses and versus the alternative dresses here. So, all right. Okay. However, we just use our data to fit this null model to see if it fits or not. All right. That's easy, right? So we just compare our data with this. The population mean of this non-distribution, and we're gonna create a t-statistic, which will help us to calculate a p-value, and with the p-value we can easily make a decision. Either we accept the null hypothesis or not, right? Is that clear? So this is how we do this hypothesis testing. And so now let's go back to our business. So here we are doing this. So we construct a word test, which is a chi-square, which is chi-squarely distributed. All right, and so So can anyone tell me what do we test by constructing this ratio, this word test? So what do we test? So this is a little bit different from the t-test I just showed you, right? So here, think about the F2 population, and we want to find if this locus is genetically associated with the trait of interest. So I hope you still remember. So we spent like some time to discuss how we create this word test, which is a ratio of this. This is something like the signal to the noise ratio, right? So here, actually, we want to test what? We want to test this. We want to test this B. This B here, suppose we're testing the additive effects. So we want to test if this additive effects is significantly different from 0 or not, right? So if this additive effects is greater than 0, which means, okay, this locus is indeed associated with the trait of interest, right? So this is what we're doing here now. All right, so we have two distributions. See, I tried to connect this with the example. So this distribution means additive effects equals to 0, which means there's no association between this locus and the trace, right? So if this is the case, so your data should follow this chi-square distribution with the which is called the central chi-square distribution, and you're going to see the parameter for this chi-square distribution equals to 0. So this parameter is called the non-centrality parameters. If this non-centrality parameters equals to 0, which means this chi-square distribution is following a central chi-square distribution. It's like this. All right, this distribution, chi-square distribution, the non-distribution is a chi-square distribution with the non-centrality parameter equals to 0. Or this is equivalent to say additive effects is 0. There's no association. Okay. However, if this doesn't make sense, and your data shows this distribution is actually following a non-central chi-square distribution with a non-centrality parameter theta is not equal to 0, then this alternative distribution will be something like this. Okay, will be something like this. Okay, and then we have like two dresses here, right? We have two dresses here. So this is the basic theorem behind the test we're going to use for testing this major genetic effects. So the same. So I'm using the additive effects as example, but this should be identical if you want to test the dominance effects. Does that make sense? Yeah. Okay. So we are actually testing our data by using these two distributions, two dresses here. Okay. So we have mentioned there are two types of errors, right? Type 1 error and a type 2 error. Actually, these two errors are not independent. So somehow they are like, so if you want to perform a statistical test for any hypothesis, there are two types of errors, alpha and beta, and they are not independent. We're going to show you, actually, there's a trade-off between these two types of errors here. So see, still like we have two hypotheses, right? We have two distributions. We have a non-distribution and we have an alternative distribution. Okay, so remember, we always put the non-distribution on the trial. And so based on the non-distribution, just look at here. So based on this non-distribution, we're gonna find out a cutoff here to help us either accept non-hypothesis or reject the non-hypothesis, right? So anything on this side will support the non-hypothesis. We're gonna accept the non-hypothesis, right? Or if any value go beyond this cutoff, we're gonna reject the non-hypothesis. Does that make sense? Okay. All right. So how to select this cutoff is quite arbitrary. So you can choose 0.05, or if you don't think this is a stringent one, so you can use 0.01 or even lower 0.0001. But however, no matter what cutoff you're going to choose for this test, once this cutoff is determined, so you're going to automatically determine the type 2 error. So what is the type 2 error? So once you decided this cutoff for the non-distribution, you also decided the beta error for the alternative distribution, right? Do you agree with this? So if you determine this cutoff, then when you look at the alternative distribution, so this region actually represents the beta. Why? Even the data is from the alternative distribution, but it is likely that it can go beyond this cutoff, right? So even this data came from the alternative distribution. If it goes here, so the data goes here and go beyond this cutoff. So, but you don't worry about the alternative distribution. In the hypothesis testing, you just fit your non-distribution, right? If the data go beyond here, you're going to accept the non-hypothesis, which is wrong. Can you follow me? Okay, good. So that area, the yellow area, is the error. It's a type 2 error, right? Okay, now what is the 1 minus the type 2 error? So it's actually this area, right? This area represents if the alternative hypothesis is true, what is the probability you're going to successfully reject the non-hypothesis? So that's the power. We want to increase this power, right? So in the future, when you design your own genetic test or experiment, you always want to increase this part. This is the power, because for any locus, you want to detect the potential association between this locus and the traits, right? So, which means you want to increase the probability that, given the alternative hypothesis is true, I want to successfully reject the non-hypothesis. So that's the power, right? But as I just mentioned, so we always determine the cutoff, the rejection cutoff based on the non-hypothesis, non-distribution here. But once you determine some specific cutoff, you simultaneously, the type 2 error or power has been determined. So if you want to reduce, so here, this is the key point. If you want to reduce your type 1 error, so type 1 error is actually what? Is actually the red area, right? Can you see this? The type 1 error is the red area. So if you want to reduce this, so what you can do is, like, you're gonna make this cutoff more stringent, right? You're gonna remove the cutoff on the right-hand side. So this now the rejection area is here. It is less than 0.05, right? But see what happened if you move your cutoff from here to here, then you're going to increase your type 2 error, which means there's a trade-off between the type 1 error and the type 2 error. Does that make sense? Okay, very good, very good. Okay, so just like this, if you use a more stringent, you're going to increase your type 2 error, and you're going to reduce your statistical power for your test. So this is very important, and it is a key point. So in the future, when you decide your cutoff in your experiment, you need to think about the trade-off between the type 1 and type 2 errors. You need to find a proper cutoff, which can guarantee a small rejection error, but also guarantee you have enough statistical power for detecting the true signal from your experiment. Okay. So this slide actually shows you how we can control this two errors here, right? In the future, when you do your own experiment, so you can use some of these strategies to help you to put some control on the error. So, for example, so this is like the original test. So we are comparing this non-distribution with the alternative distribution. So one thing, if you do not want to change your alpha type 1 error, so how can we increase the detection power? So one way to increase our detection power is like if the difference, so we can choose the test that the difference between these two distributions are large. So if you can see, so if the true difference between the non-distribution and the alternative distribution is larger, then even we do not change the type 1 error, we can increase the detection power, right? So this, for example, there's two genes, gene 1 and gene 2. Okay. And so in this, for this, so those two genes are potentially differentially expressed between the cancer and the normal, let's say. However, the difference for the first gene, the difference between the control and the cancer and the normal is like, for example, is 0.1, some unit expression level. But for the second gene, the difference between these two groups are 2 units. And if you can only choose one gene for further validation, which one will give you more hope? Of course, the second one, right? Because the difference between the control and the treatment or the cancer or normal are larger. So which means like, even you do not sacrifice your type 1 error, you can still guarantee a good statistical power for detecting the difference between these two groups, right? So this is one way. So you choose the test with bigger difference between the non-distribution and the alternative distribution. So this is one way. So this is one way you can increase the power. Another way is like this. Can anyone tell me what does this mean? So, all right. So, if you, yeah, go ahead.
Log transformation.
One way, yeah, that's one way. So you can change your scale, but usually this will not change the test results in most of the case. The reason why you see like the distribution of these two non-hypothesis or alternative hypothesis becomes smaller, the variance, right? The variance becomes smaller is because you increase the sample size. Once you increase your sample size, you can get better estimation of your population mean. Then, yeah, so this will be another opportunity for you to increase the statistical power. So does that make sense? If you increase your sample size, you're going to make your distribution sharper. And even the center of this two distribution do not change, but the overlapping area become much smaller. And even you do not sacrifice your type 1 error, you still can get a very good statistical power for your test. Does that make sense? So either way, you choose the test with the bigger difference between the two hypotheses. Or if this is not possible, you can increase your sample size to increase your power. So this is always true. So if you have enough sufficient funding, so you can always include more samples in your study. However, this is not always the case. So then you have to use some like other strategy to help you to help you make your experiment better. Yeah. Okay, very good. So I hope this is clear to everyone. Okay. All right. So this slide shows you the relationship between the z variable, which is, so if z is a normal distributed, is a random variable which is normally distributed. This is a standard normal distribution. Okay, and the relationship between normal distribution and the chi-square is like this. So if you square a random variable of z, which is a normally distributed, so this will be a chi-square distribution with 1 degree of freedom, right? And if this normal distribution is centered by 0, so this is important. Okay, then this chi-square distribution is a central chi-square distribution with this theta equals to 0. What is the theta? Can anyone tell me? Do you still remember? The non-centrality parameters for chi-square distribution. So this is the relationship, all right? Okay, now it is very straightforward for us to understand. So if we have a z prime, which is also normally distributed, however, this normal distribution is not a standard normal distribution. Although it has the variance equals to 1 as well, but if it is centered at 1, so this is a normal distribution with the mean equal to 1. And so this z prime square is also, if we square this z prime, this is also a chi-square distribution with degree of freedom equals to 1. However, this delta is not equal to 0. So we call this is the non-central chi-square distribution. And we're gonna use this feature. So this is not required, okay? So this is for your information. Because sometimes when we do the power analysis, we have to use this relationship. We have to use the normal distribution to help us to calculate this non-centrality parameters. I just want to show you how we do this. And so I will not put any test on the final exam. And in this week's assignment, I'm going to give you the code by which you can calculate the non-centrality parameters to achieve the power calculation, given some specified alpha and beta value, the type 1 and type 2 error. Okay, is that clear? So what's the relationship between the normal distribution and the chi-square distribution if this normal distribution is centered by 0 or not? Okay, good. Okay. All right, so this just gives you some like idea about the chi-square distribution. So if lambda equals to 0 means the central, right? Central, so it's very close to here. And the degree of freedom, so if we add up like 20 z's together, independent z's, so this is the distribution. However, if you see, as this non-centrality parameter increase, you're gonna see the distribution is moving towards the right end, right? So which means the center of this chi-square distribution is moving towards the right-hand side. Yeah. Okay. And usually when we do the testing, so just think about like, so when we do the testing with the b square divided by the variance of the b estimation. So we are using two chi-square distributions, right? One is the distribution. One is the chi-square distribution is set with this. One is the central. I mean, I'm sorry. One is the central chi-square distribution, which is the non-distribution, and we always use another one. For example, this is the alternative distribution, which is a non-central chi-square distribution. So we're gonna put our data on this test with two different chi-square distribution. All right. Okay. All right. So power calculation. So this is very similar to the normal distribution. So I think in one of our assignment, I gave you the R code by which you can easily calculate the probability of a normal distribution given some critical values here. Here is the same. So we can use the R to help us to calculate the probability or the cumulative probability given a specific chi-square statistic. If this is a central chi-square distribution. So this is central chi-square distribution. So we can calculate the area under the curve on the right-hand side. So what is this? Can anyone tell me? What is this area under the curve here? So this, yeah, anyone? What is here? This is something like the normal distribution. We use a cutoff, and this is the 0.05, right? Think about this. This is the same. So this is actually the p-value we want to calculate, right, in your test. So for example, you want to put your data on this distribution, non-distribution. And if your data give you a chi-square value here, so what is the probability for this test? So this is a very common situation in hypothesis testing. So given this non-distribution, if you can calculate your test statistic like this big, so you're going to calculate the area under the curve on the right-hand side, right? So that gives you the p-value. So if this p-value is less than 0.05, which means you're going to reject the null hypothesis, right? If this is too small. Otherwise, if the p-value is greater than 0.05, which means so there's a strong evidence to show your null hypothesis is making sense. So you're going to accept your null hypothesis, right? All right. So this is how we calculate this area, and I'm going to show you the code in the assignment. And in the future, you can take advantage of using this scheme to calculate, or you can use the R function to find this cutoff. So if we want to use a 0.05 as a cutoff, what is the critical value for this chi-square statistic? So we can also use R code to help us to calculate this critical value. Okay, now this is for the theta equals to 0, right? This is for the central chi-square distribution. And we do the same thing for the non-central distribution, chi-square distribution. So the non-central chi-square distribution is similar to the central chi-square distribution. However, it is just moved towards the right-hand side. Now we have two chi-square distributions to compare. So this is the basic theorem behind the hypothesis testing. And the same thing, once we definitively define this non-central chi-square distribution, we can either calculate the p-value or we can calculate the cutoff, the critical value for any p-value here. So this is the flow chart. This flow chart actually shows how we do the power calculation. So suppose when you do the power analysis for your experimental design, so first we need to specify the alpha value, right? So usually we put alpha equals to this 0.05, and then based on this, we can easily find the critical value for this alpha value. So if you look at the chi-square table, you're going to see the degree of freedom equals to 1 for the central chi-square distribution. If alpha equals to 0.05, the critical value should be 3.84, something like this. Okay. And R can help you to calculate this as well. So in the future, you don't have to look up the table always. Like you just simply type a line of command in R, and it can give you this value. And okay, now if you have this theta, this is associated with the power. So I'm going to show you later, and then you can easily calculate the type 2 error actually based on this alternative distribution, the non-central chi-square distribution, right? And once you can calculate this type 2 error, the power is easy. It's just 1 minus this. So this is how we calculate the power. So given some specific sample size, what power can you achieve by doing this experiment? So this is how we calculate the power. I'm going to show you an example shortly. All right. Sometimes we have a question in an opposite way. So if we already know the power that we want to achieve, so what is the sample size required for achieving this power, statistical power? So this is another power analysis in a different direction, right? To achieve power of 0.9, suppose. So if we want to see, like, if our non-hypothesis is true, if our alternative hypothesis is true, so what is the probability for us to successfully reject a non-hypothesis? So if we want to achieve the power of 0.9, so what is the required sample size? So this is how we calculate this. All right, as you can see, following this flow chart, we're gonna be able to express the required sample size n equals to this. So this is the expression, and this is the non-centrality parameters for the alternative distribution, and this variance of the design matrix. So we're going to talk about this. This is something that we can control, the variance of the X, because in F2 design and the backcross design, we have shown the variance of the X is different, right? The variance for F2 is 1/2, but the variance for backcross is 1/4. So this variance is larger than backcross, which means it's more efficient. To achieve the same level of the power, F2 requires less sample size, smaller sample size. Okay, and as you can see, if your genetic effects is larger, so A means the additive effects, right? If this is larger, the required sample size becomes less, right? So if you want to test a loci with a larger genetic effects, then you don't need much sample to achieve that. So that's the other way to understand the relationship between the genetic effects and the required sample size. Any questions here? Okay. All right. This slide also shows you the relationship between the power and the required sample size. we just introduce another concept here, right? So what is this? Heritability, right? This is the broad sense heritability, the capital H score. So, and this is how we define this heritability. The proportion of the total variance observed in the phenotype can be explained by genetics, right? And if you just do a little bit like rewriting, you can write this into this situation. The heritability is actually associated with the real genetic effects, right? If your genetic effects becomes larger, and this is also larger, and this, the entire thing ratio is more close to 1. So this will increase your heritability if you increase the genetic effects for a locus. And we can use this relationship to rewrite this equation. So this is the equation to the formula to calculate the required sample size for your experiment. And finally, you're going to see this, right? So if you increase the heritability, or if you want to analyze a trait with higher heritability, which means like if this is larger and this will become smaller, then the required sample size is becoming smaller, which means, so if you study 2 different traits, these 2 traits have different levels of the heritability. So one with the high heritability, the other one with low heritability. So for the high heritability, for the trait with high heritability, you don't need many sample to detect the QTL, the associated loci, genomic loci, right? But the trait with low heritability, that's a challenging one. So probably you have to apply more grant from NSF, more money from NSF to support your hypothesis. You have to, you have to increase your sample size to detect the smaller, the trait, the QTL for the trait with smaller heritability, with lower heritability. Okay, does that make sense?
Dr. G, I have a question.
Yeah, go ahead.
So for the F2 design, it would be more efficient, but it would possibly take a longer time in practice, correct?
Let me think. Yeah, the first part is correct. Yes, definitely F2 is more efficient. But in terms of like the experimental, let's say, so F2 is backcross, which means like we always start from 2 parents, right? A1, A1, A2, the same. And we got the F1, which is A1, A2. And then for the second step, so I think in terms of timing, the same. In terms of the experimental schedule or timing, it's the same, because the difference between these 2 designs is here, right? So depending on whether you cross this F1 back with 1 parent, or you just do the cross among this F1. So yeah, I think that in terms of the experimental, the real experimental part, I think the same. But
just F2 is just a little more complicated, right?
Yes.
Yeah, you just have to account for more error.
That's right. Yeah, I agree with you. Yes. Yeah. So then for the second part of the question, yes. So probably it will be more complicated, and you're going to suffer more when you deal with F2 design. Yes. But yeah, everything will be paid back if you put more efforts in that, right? Yes.
Yeah, I just see this because if you need such a small sample size with a really heritable trait, I mean, it seems sort of not even a question about in a breeding experiment.
Yeah. Right. Yeah, that's a good question. Thank you. Okay. Any other questions here? Okay. All right. So yeah, this slides just show you why F2 would. So by doing F2, you're going to get more, right? Because because this part I'm sure I assume everyone is comfortable with this. So in the final exam, if I ask you, all right, so yeah, please compare F2 versus backcross, and what's the difference? So this is the difference, right? Because in F2 you're gonna see all three genotypes, but in backcross you only see two types. And if you use the same coding for the X variable in the linear model, so you need to know how to calculate the variance of this X, right? And the variance of X in two design. And you need to get this. So the variance of the X variable, this is additive, in the F2 equals to 1/2, but the variance of X equals to 1/4 for the backcross. Now, the key point is like, so if you use this power calculation to calculate the required sample size for each experiment, you're going to see this sample size n is inversely related, right? Inversely related to this. So the larger variance in the design matrix will give you better power. So in that case, you're going to need less sample to achieve the same level of the power. Does that make sense? Mm-hmm. Okay, very good. So this might be a question showing up in your final exam. Mm-hmm. Okay. All right. So okay. So this is very complicated. So it's okay. So if you cannot like easily understand this, but it's fine. So I'm gonna just leave this up to you. So you can read the slides and find more material to help you understand. But basically, this is how we calculate. This is the formula we're going to use to calculate the non-centrality parameters for the non-central chi-square distribution. So as you can see, the association between this with the z variable. Z is a normally distributed. So this is a standard normal distribution. Z is standard normal distribution. Mean equals to 0 and variance equals to 1. And if we can easily calculate this critical value and this critical value, right? So if we want to define an experiment with alpha equals to 0.05, and if we want to achieve beta, 1 minus beta, which is the power, equals to 0.9. So what is the non-centrality parameter for this chi-square distribution? All right. So this is easy because we can easily find the critical value from normal distribution. This equals to 1 minus 0.025, right? If we use the 0.05. This is like this. And this is the critical value when the p-value equals to this. I'm going to show you. So I'm going to quickly show you how we do this. Let me stop sharing here and oops. Okay. Okay, not this one. A second. Okay. So can you see my screen? All right. So I'm still working on this week's assignment. So I just started. And here, I will give you some R code like this. So you can, in the future, you can follow to calculate the power. So for example, the first part is like how we can calculate the non-centrality parameter of a chi-square distribution with specified alpha and beta. So suppose alpha in this experiment, so if you want to design experiment with alpha equals to 0.05, that's the rejection cutoff, right? And if you want to specify your beta equals to 0.1, which means like the power will be 0.9, right? So you can use this quartile normal function to find the cutoff for this two. So this is how we calculate. Let me stop sharing this one and show you this. Oh, not this one, sorry. This one. Okay, so can you see this? So the non-centrality parameter is equal to this. This is Z1. We want to calculate the Z1 here, and this is Z2. If we can calculate Z1 and Z2 given this alpha and the beta, so we simply add up these two and calculate the square of this sum. This will give us the non-centrality parameter. Okay, so this is exactly what I do in the code here. Okay, so the first one is calculate the Z1. So use the quantile, right? And then the second one is Z2. So if you just do this, I'm going to show you Z1 equals to something like this. Z2 equals to this. And then this is the centrality, non-centrality parameter you're going to calculate. So what is this? Yeah, that's the non-centrality. So this is not required. I just show you the code that you can use. So I think it is very hard for you to understand the relationship between this, but it's okay. It's not required for you. You only need to know, yeah, you can use something like this to help you calculate the non-centrality parameters for an alternative chi-square distribution. Does that make sense? Okay. And so this is how you calculate the beta. In this situation, the beta must be 0.1, close to 0.1. Yeah, that's close to 0.1. And if you want to calculate the power in this situation, that power gives you 0.9. So yeah, that's correct. All right. And this will be part of the practice code that I'm going to give you for this week. All right. And let's continue. Okay, so it is quite complicated here. Just spend some time to review the lecture slides after class. And important, very important, please read the textbook. So textbook can give you a lot of more information to help you digest this materials better. Okay, all right. Now, so if we want to test each genetic effects, either the additive effects or the dominant effect, so we can use this as a non-distribution, right? The central, so this theta equals to 0, and we can use this to calculate based on the power, based on the alpha and the beta specified value, so we can calculate the non-centrality parameters for the alternative distribution. And so this is how we calculate this non-centrality parameters for testing one genetic effects only. So this is for the additive, or we can test both effects, the additive and the dominance, by adding these two non-centrality parameters together. All right, this is just for information. Okay. Okay, now look at the example. So this is a very easy example. So it could be some questions for the final exam. So as you can see, it doesn't involve a lot of like complicated calculation or derivative, just based on some like concepts that we should know of, and based on some like information provided in these problems, how can we do some simple power calculation for an experiment. So for example, here, let's look at the first example here. So suppose, so here we want to calculate the statistical power. So we want to calculate power, right? Omega equals to 1 minus beta. So beta is type 2 error. All right. If we want to specify, so let me see. So if we want to, so how can we calculate the statistical power to detect a major gene effects? So here A equals to 5, which means the additive effects equals to 5. Okay. All right. And this is a F2 population. And we already have the information about the sample size. So N equals to 200. And here we specify alpha. Alpha equals to 0.05. And we suppose we already knew that the residual variance equals to 400, right? Because based on this question, so how can we calculate the statistical power? So here we need to derive some like a hidden information here. So if this is a F2 population, so we can easily calculate the variance of the design matrix, right? So do you still remember? So the Z actually here we use X. X equals to 1 for the first genotype, right? A1, A1. And 0 for A1, A2. And minus 1 for A2, A2. And this two, this is F2 population. So the associated probability for this two will be, this one is 1/4, this one is 1/4, and this one is 1/2, right? Okay, so based on this information, you can easily calculate the variance equals to 1/2. So this is very important. And now, so based on this information, we can easily, so the alpha equals to 0.05, so we can specify this critical value, right? 3.84. So this is how we can use R to help us to do the calculation. And the non-centrality parameter will be equal to this. This is the formula we can use because we already knew this A, we already knew this sigma square. So this is the given information. So this is a very easy, straightforward problem. So it could be some, I could give you some questions similar to this in the final exam. So basically, I will also provide, since this is a closed book, so I will also provide the formula. So, but you need to understand the meaning of each parameters here, right? So we have this, and the N is given, and this is the part you need to calculate, which is 1/2. So after you plug in all these values, you can get this value for the non-centrality parameter for the alternative distribution. All right, now, given this, then it's easy, right? Because the statistical power is actually W power is 1 minus beta. And this beta is the area. So we have two distributions here, right? Once you specify the cutoff for the non-distribution, you automatically specify the area of the beta, right? So based on the alternative distribution, you can easily calculate the area under the curve on this area. So this is how we calculate the beta. So this is this. And if you use 1 minus beta, that's the power. Okay. All right, any questions here? I think this is another example here. They're very similar. So the second example is like, okay, so here, so this is a very typical question that probably in the future you're gonna ask yourself if you want to do your own experiment, or if you want to help your lab member to calculate the required sample size. If you knew these traits can be explained by a gene at a locus, and that gene can explain 3% of the phenotypic variance with a power equal to 0.9. And here we still use the type 1 error alpha equals to 5%. So based on this, so this is the description of this problem, and then we want to calculate the required minimum sample size. So we just we try to arrange the known information. Alpha equals to this, beta equals to this, right? 0.1, and heritability equals to this. And we have this formula here, right? So in the final, if I ask you a question like this, I'm going to give you this formula, but you need to know how to plug in those numbers to calculate this required sample size. And this value is actually, I just showed you in R coding. So how we can use the normal distribution to help us to calculate this non-centrality parameters, right? Which is about like 10.5. Okay, I think I'm done with this chapter. And any questions before we move to the next chapter? So we spend some time on these two chapters because this is the major point. We try to understand. So I try to help you understand. So how we can test a single locus to see if this locus is associated or is responsible for the phenotypic variation, right? So once we understand what is going on in testing a single locus, so we can easily extend our idea to test the entire genome. So the same, we just repeatedly use the strategy to test each locus with the genetic information, right? The genotype information. Because right now with the sequencing or genotyping array, we can easily get the genomic information for each of the millions of the SNPs or some genetic variants, and we can use that as the genotype like this. F2 design is a easy and standard design, but in the future, if you get a natural collection from like people like citrus, so the allele frequency is not following the F2 design, right? So, but with all this information, you can still use the same testing scheme to test each locus along the genome, and then this can help you identify all possible genomic loci that are responsible for the trait of interest. So it's very important. And so we talk about the test, how we test the major effect at each locus. And we know, now we know the theorem behind it. So we're actually comparing two chi-square distributions, right? The non-distribution and the central one and the non-central chi-square distribution. So this is how we understand this. And based on that information, we can also calculate the power or the required sample size to achieve a certain power. So this is all we want to know for testing a single locus. In the future, like for the remaining chapters, so we just apply this strategy to do the GWAS, to do the QDL mapping. So we will move very fast because I assume like everyone is comfortable with this. For those advanced schemes, I will not put any questions for the later, for the for the later chapter, so I don't think I will put a lot of like questions. We will put I will put a lot of questions on the final exam. The questions showing up on your final exam will mainly come from probably the first 8 chapters. So this is why I would rather move very slowly to make sure everybody feel comfortable with the most important, the basic and the fundamental knowledge. So once you understand this, in the future, even you read a very advanced article that is related to the quantitative genetics, it's easy because those advanced study actually is a build up, is an advanced method that is built up using these blocks. So if you have already know this, the small things, the basic things, it can easily help you understand their advanced methodologies. So, all right, let's stop. Let me see. We can briefly start the next chapter. So, all right. So I just give you a start for the chapter 7 and 8. Okay, so next time on Thursday. All right, so I'm still debating myself. So Thursday, Mariano and I and our lab will will organize a pomegranate tasting event on Thursday. So probably so I'm thinking about maybe we do not have a lecture on Thursday because I need to be there to help Mariano and my lab members to organize this events. So all of you are invited to come and taste some like different variety of the pomegranate and give us your data. So how do you like each different like fruit? All right. So maybe I will send out a announcement whether we're gonna have the class or not. But likely we're gonna miss this time and we're gonna continue our lecture from next Tuesday. All right. So next time we're going to talk about the segregation analysis, which means like, so this is a F2 population, right? If we have the genotype and the phenotype data available, so we can easily use this linear model to test whether the additive effects or dominance effects or both exist at this locus, right? So this is what we have learned. It's easy for us now. We're expert now. But in this chapter, more challenging comes. Like, so how about like we do not have the genotype data here? We just observe phenotype data. Can we still test if this population has some like a single gene effect for this phenotypic variation? So, okay. And next time we're going to talk about the mixture model, because the mixture model is a very, very good advanced idea, which was raised by this gentleman, Fisher. So he actually used the example of iris flower data to show how we can do the clustering based on the phenotype of this. So actually, this is a population, and this population, iris, actually consists of 3 genotypes. So if you plot the data based on the petal length and the petal width for each of these individuals, you're going to clearly see the 3 different distributions, right? So how can we use statistical model to segregate, to differentiate the 3 potential subpopulations? So this is what we're going to talk about from next week. Right. Any questions? So I think I'm going to stop here. So we're going to use, so if you have any questions for the lecture or the practice assignment, so we're going to talk about this. We're going to use this time to discuss. All right. Any questions that I can help? Perfect.
Thank you, Dr. Gia.
Thank you all. So again, so we're gonna have so let me make the decision. So we don't have lecture on Thursday, so we will have like beautiful like pomegranate tasting events in the morning and in the afternoon. We have 2 sessions. So Mariano, do you mind if you send out the information again to this class? So
Sure.
everyone will be invited. And
Yes.
yeah, you can also bring your friends to the events. So we're gonna continue our lecture from next Tuesday.
Great.
All right,
Please
thank
come.
you.
Please come. Bring
Yeah.
your friends, everyone.
Yes, please.
Thank you.
Thank you for your support for supporting our events. All right,
Thank
bye
you.
everyone.
Bye-bye.
Yeah, bye.